Hey everyone, welcome back. Today we're doing invert binary tree. For this question, we're given the root of a binary tree and we have to invert the tree and return its root. So in this case, inverting the tree means swapping the left and right child with each other. And for our viewers who are new to the data structure of binary trees is a graph-like data structure where every single node in a binary tree consists of a value as well as a pointer to a left and right node. So in this case, you can see that we have a definition for a tree node, and over here we can see that we have a value. In this context of this question, the value contains a number or an integer to be specific, and it also has a left and right attribute pointing at two tree nodes. So these left and right attributes can be none or they can be pointing at another tree node. So for this question, if we get an example of 4271369, how we read this is, in this case, this is pretty much this is an in-order traversal. So we start off from 4 and we go down to 2, and we also have 7, and we also have 1, 3, 6, 9. I see. This is not an in-order traversal. This is actually a layer by layer. This is a layer by layer traversal. So 4 first, followed by 2, 7, followed by 1, 3, 6, 9. So as for how do we get this representation, we will encounter that in subsequent Leetcode videos. We'll be using an approach called breadth first search, but I digress. In this case, if we are given such a binary tree, if we are to invert it, notice that we are swapping the left and right child. So 7 will now be the left child of 4 instead, and 2 will be the right child of 4. Similarly, for 7, we can see that previously 9 was the right child over here. Now it's swapped to the left. And similarly, 6 was previously the left child of 7. Now it's swapped towards the right child. Similarly, that is the same for 1 and 3 over here. So that's pretty much it. So one way we can do this, I guess before we go through the implementation, let's go through another example. So in this case, you have 2, 1, 3. In this case, we invert them by setting 1 to be the right child and 3 to be the left child. And for the final example, if root is none, then we will just return none. And in this case, the number of nodes in the tree is in the range of 0 to 100. So it is possible for us to receive a root that doesn't have any nodes in them. On top of that, every single value in every node ranges from -100 to 100. So sorry for jumping the gun just now. I will jump straight to the suggested implementation earlier. But one way we can do this is by using depth first search. In other words, using recursion to recursively check a root and swap the left and right child. And if the left child or the right child exists, we will recursively call invert tree on itself as well. So that's pretty much the idea of this solution. So in this case, I guess it would be easier for me to code it out first before we start tracing, since we are using recursion in this case. So the first step is to check if root is none, then we will return none. Else, in this case, we can leave this statement as a guard. Once it passes that guard, then we are guaranteed that the root is not none. So what we can do is we will just do root.left, root.right equals to root.right, root.left to do the swapping. And once this is done, we can do if root.left exists, then we can call invert tree. We can do self.invert tree, do we? Yeah, self.invert tree. And we can pass in root.left as the root. And similarly, if root.right, then we also do self.invert tree, root.right. And that's pretty much the solution. And once we're done, we will just return the original root. So that's pretty much the solution over here. So let's try it out with this test case over here. So the first root over here will be 4. So we'll pass in 4 over here. Since this is false, root exists, so we will skip line 13 to line 14 and we will go into 16. So I guess it's also good to show you the call stack. The call stack is an underlying data structure that contains the that stores memory on function calls. So right now we've just invoked invert tree on root. So this is the current call stack. So now we are evaluating this. And let's continue. So we are currently at this node over here. So we swap root.left and root.right with root.right and root.left. So now root.left is equals to 7 and root.right is equals to 2. So after that, since left and right exist, this is true. So we will first call self.invert tree on root.left. So notice that it is calling itself now. So now we are pretty much moving towards 7 over here. So we're currently we have just did a depth first search traversal down to node 7. And now the call stack would contain this invert tree. Actually, let's just put the root number here. And now we are currently at 7. So the function call for invert tree 4 is not done because it is still evaluating line 24. So we are currently evaluating invert tree 7. So now we're at 7. Root in this case is 6 and root.right is 9. And we are currently in this state over here. So root is not none, so this is false and we skip this. And now we swap the root.left and the root.right, so we get 9, 6. And now we check if 9 and 6 are valid. In this case, root.left exists, so this is still true as well. So we will call self.invert tree on root.left, which is 9. So now we will add on an additional function call, which is invert tree on 9. And we are now going to evaluate this. So similarly, invert tree 7 is not done yet, so its function state and memory used for keeping track of the function still exists on the call stack. We're now evaluating the top of the stack, which is invert tree 9. So now root is now set to 9, and in this case root.left is none and root.right is none. So in this case root is not none, so we pass this. And we do the swap anyway, but there's no net effect over here because they are both nuns. And in this case, since root.left is false, this is skipped. And root.right is false, so we skip it as well. So just to take a step back, we're currently at this state over here. So 9 is actually here. Sorry, we're actually here, but we're pretty much at a leaf node over here. So we don't call this because left is none, and similarly we don't call invert tree on right because right is false. In this case, we'll return the root, which is 9, and we are done with this iteration. We will pop this off the stack, and now we return invert tree 9 back to the result. Now we are pointing back at invert tree 7. We have now traversed down to 9 and came back up to 7. So now 7 currently contains, if I'm not mistaken, this is, okay, as you can see, it got a little messy. I guess I should keep track of the root.left and root.right over here as well. So over here, root.left was swapped. So in this case, root.left for 7 is 9 and root.right in this case is 6. And for 4, we swapped them already. So now this is 7 and this is 2. Okay, so now we are evaluating invert tree 7 and we are at line, let's define the line as well. So this is currently at line 24. So we finished at line 24 earlier. So we continue, we are here, and we return, and we got the result 9 back here. So we got the result 9 back, but there's no need for us to do anything to it. We didn't assign anything. So we just continue over here. And now we invoke self.invert3 on root.right, which is 6. So we will call another invert 3. Now this is at line 27. And let's do invert 3 on 6. Now let's look at 6. Root.left is equals to root.left is now equals to none, and root.right is equals to none. So root is not none, so this is false, and we swap the two nuns together. In this case, there's no net effect as usual. And because root.left and root.right, we pretty much did a traversal down here. We came back up, and now we did a traversal down to 6 for our viewers, in case this is not clear. But in this case, both of these, line 24 and line 26, for this function called invert36 are false. So we skip calling invert3 again, and we return root. So invert3 returns the result back to invert3 7, and now we will set root.left back to 9 and root.right back to 6. So this is evaluated, and now root.7 returns control back to invert3 4. So now this is popped off. We pretty much did a depth first search traversal down to 9 earlier, back to 7, back to 6, back to 7 again, and now we are back to 4. So now we are here. We have just finished line 24, and now let's set this back to the root value. So this is pointing at node 4. Root.left is now pointing at 7, and root.right is now pointing at 2. And we are done with line 24. We hit line, oh sorry, I meant line 23, but you get the idea. We were evaluating this line over here earlier. I think the line shifted because I deleted something, did I? But anyway, you get the idea. So we are done with this, and now we will hit line 25. So we will try to call invert3 on root.right. So we are doing a traversal down here now. So we will be calling invert3 on 2, and root.left in this case would be, so we are currently at line 25. Okay, I mean, you get the idea. I'm shifting lines here as I trace, but you get the idea. So root.left in this case for 2 is root.left in this case for 2 is 1 and 3 initially, this previous state over here, and this is false. Root is not none, and we swap the left and right. So now left is now assigned to the right node instead, and the right node is now assigned to the left node instead. And now we call invert3 on, okay, so invert3, we're currently at line 23. Okay, line 23 to line 24, but I'll just put it at line 23. So we are now at line 23, and we call self invert 3 on root.left. So we will call invert 3 on left. So this is pretty much it. Let's do this. Root.left and root.right is now assigned to none, because for this node over here, it doesn't have any children. So now we are here. This is our current execution. So now we're at line 20 for invert 3. So we've just went down this way. We've just did a depth first search traversal down to node 3 over here. So root is none. Okay, so now we swap left and right together on line 23. No net effect because both left and right children are none. And this is false because root.left is none and root.right is false. So we do not invert any 3, and we return control. And we finish this function invocation on invert 3. So we finish this, and now we are back at invert 3 node 2. So we just traverse back to node 2. Now root is equals to 2, left is equals to 3, and right is equals to 1. So we were done with the function invocation here on line 24. So now invert 3 on 2 will now be at line 25 or line 26. So we are going to call self.invert3 on root.right. So let's call invert3 on root.right. So now this is 1, left is none, and right is none. So we are here. The left and right child is none. So in this case, this is false because root exists. And we do the swap as usual, left and right. There's no net effect because both the left and right child of root 1 node here is none. this will be false because left is none. Root.right is false because right is none. And we will return an invert tree over here and pass control back to invert tree 2. So now we have just traversed back upwards from 1 to 2 and we are here. So the root is now 2 and the left is 3 and the right is 1. So over here, we were just done with this invocation. So invert tree 2 will now terminate and return control back to invert tree 4. So we are here, 7 2 line 25. Now we're at root 4, 7, and 2. And we just finished our function invocation on line 25. And on line 27, we will terminate the root, which is pointing at 4. And this ends. And that's pretty much the trace. That was really intense, but I felt that the tracing was necessary, especially for our viewers who are new to this concept of depth first search. So in summary, if I have to summarize our strategy over here, we're doing a recursive implementation of swapping the left and right children of the current node. And if the left or right child is not none, then we will recursively call invert tree on the left and the right child as well. The net effect of that is that if you start off at node 4, we will go down to 7. 7 will make a function called invert tree on its left child, giving us 9. But because 9 has no children, it will terminate. The whole function will terminate from line 9 to line 21 and it will pass control back to 7. It will do the same function called invert tree on its right child. And once it does the inversion, the control is passed back to 7. And 7 ultimately terminates, passing control back to 4. And this continues for the right child as well. We'll go down to 2. 2 will call invert tree on its left child, technically doing a depth first search down to 3. 3 will terminate, passing control back to 2. 2 will continue and make a call to invert tree on the right child. And this function will terminate because its children are none. It will go back to 2 and 2 terminates, passing control back to 4. So in summary, we did a depth first search to invert the children of every single node in this graph. And this is pretty much the net effect of that. So as you can see, recursion saves us a lot of lines of code. So let's look through this again. We traced all of this, so this looks fine. Let's run this against some test cases. This passes, and let's submit this. Okay, and that's pretty much the answer. So in summary, if n is the number of nodes, then the time complexity is O(n). Notice that to invert the tree, we have to go through every single node in the tree and invert the left and right children. So it makes sense that we have to go through every single node for this algorithm. For the space complexity, as you saw earlier, we use a call stack. And you can see that roughly the length of the memory that is used for this algorithm is the size of the call stack. In other words, how many function calls do you actually make, and such that the call stack still remains full. So you can estimate the space needed in the call stack to be the depth of your binary tree. So if your binary tree has a depth of, let's say, 3, in other words, a distance of 3 away from the root, then in this case, the depth would be, d will be equals to 3. But in the worst case scenario, binary trees can be imbalanced. So that means your nodes will all be on the left. Let's say you have a binary tree with 9 nodes, but each of these 9 nodes, like the nodes only have a child on the left. So the binary tree is skewed all the way towards the left. Let's say you have a binary tree of 3 nodes, let's say. So let's say you have 4, 7, and 9. That is a binary tree, but that is skewed to the left. It has a depth of, let's say, actually depth of 2 in this case, for 3 nodes over here. But in this case, we can see that the depth would just be n minus 1, where n is the number of nodes. So in this case, in the worst case scenario, if the tree is skewed, then that is the worst case scenario. So d is equals to n minus 1, or roughly O(n). So the space complexity in this case would be O(n). In other words, the call stack depth, the number of the function calls that you make when you do the depth first search, will be O(n) over here. So the space complexity for inverting a binary tree will be O(n). So that was quite a mouthful, but I hope that this was still helpful to you. If you like this video, please give us a like and subscribe, and we will see you in the next video.